Okay, we're going to do an exam review today. So no new material. This is just we'll go through some mostly example problems for the content for exam one. If you haven't checked the web page yet, then that would be a good thing to do because there is not on today's date. Today's date we'll just have the link for the video plus some older ones if you want to look at other exam reviews. There's this PDF of an exam review, which is just a kind of walkthrough of an older one that I did. I don't know if we'll do these exact problems again or not. We might do some of these. There's that on there. But if you go to class 10, so that's the actual exam day. So we go to class 10, then, well, there'll be a Zoom link here once it's set up for you to log into so that we can do the exam proctoring. But down here, these two, exam reference 1 and exam reference 2, those are copies of the reference material from the book. So if you don't have the book or you just want just the pages and not the whole book, then you can use those. I would print them out, although they're scans. I believe they're scans from like a copy machine. So they're not super clear this tiny little writing. So you do have those, but check them beforehand to make sure you can actually read them. And if not, then get your textbook. This exam outline is not like a problem by problem breakdown, but it's very close, very similar. So this is the way I set up the exams, where the first content is they're questions. They're not like calculations. They're content questions. And so there's about 10 points, I think exactly 10 points, of just content question things. It might be fill in the blank or label something. Remember, you have the stress strain diagram that you have all the different ultimate strength and yield strength and all that kind of stuff. Might have to label that. So there's 10 points of that. And then the other 90 points are broken up into these fundamental questions where there's more of those. These are all 6-point questions. There's more of those. They are usually one-step problems, maybe 2 steps, but they're more fundamental. So they're just calculate the stress given the force in the cross-sectional area. They're very direct, I think. And then the average questions, they might be multiple steps. There might be, like method of joints and method of sections. There'll be trusses on there, but they won't tell you to use method of joints or method of sections. You use whichever one you want to use. And then there's the above average ones. There's 3 of those, or 2 or 3 of those. And they are in this category here. That's where I put the 3D equilibrium equation. A design problem where maybe you're solving for the maximum force allowed, something like that. Or maybe there's a truss in there. So there's maybe 10 or so, maybe 15, I don't know, points of these harder questions. They're multiple steps. You've got to draw a good free body diagram, that kind of thing. So go through this, make sure you can solve these types of problems. They end with the content we covered last time on centroids. That's the last thing on exam 1. So you can kind of get an idea of the types of questions that will be on exam 1. And that's the, let's see, summer 20, I put 2013, hold on. I'm not on the right page here. Let's make that 2023. I even named it 2013. Huh, I wonder if it said 2013, did it? No, it actually says 2023. I just put the wrong file name on there. All right. So that's on actually class 10. So you have to go to class 10 to see that one. The exam will be here ready to take. Actually, I'll go ahead and hide it so you can't even click on it right now. But that's where you'll take the exam in Moodle, and in Zoom, you'll log into Zoom. All right. Now, what I thought we would do is just go to Webwork. I'm in optional 1. There are a bunch of Webwork problems here, and just kind of go through those, picking out some of them to work on, and use that as the review for exam 1. So let's just see where they start. I gotta log in. There could be something like this. This one is not an equilibrium problem necessarily. This one is more of finding a resultant. So that might be something we could do. I'm not sure what we've got here. 0.75. Oh, it's 75% of whatever that angle is. Okay. Um, that one is, there could be something like this where you just find a resultant. You have two forces and you've got the magnitudes of them. And you're trying to, in this case, you're trying to actually find the magnitudes. You know the resultant magnitude R, and you're trying to find these two magnitudes. So that's a little bit more than a simple problem. A simple version of this, you would know the forces and you'd find the resultant. So there could be something that simple on exam 1 as one of the fundamental level problems. So there's that. Let's not solve that one though. That's not too interesting. I think we already solved this one actually as one of our in-class examples. This one is another free body diagram type of problem. We solved that one in class, or at least set it up. I don't know if we solved it in class, but we set it up to be solved in class. Here's a 3D one. This could be like the 3D problem on the exam. Maybe that one would be worth looking at. They're a little bit longer to do, but probably worth looking at. Let's see if we can get it all to show up on one page, though. That should do it. Get all the text too. All right. Now we'll go over here and work on this one. Now, again, you won't have MathCAD to work these. You'll have to do them in your calculator or by hand. So I'm going to solve this in MathCAD just because it's not very easy for me to show you stuff in my calculator. But you can see the steps in MathCAD, and we'll do it there. I'll solve it in MathCAD in the using linear algebra, just a set of matrices to solve it, and we'll do it that way. So the first thing with this particular problem is that it is 3D, so you can tell that just by the picture. But one thing about this one that will make it difficult to solve if you don't change is where the origin is located. So they have the origin down here. And with the concurrent force systems, 2D or 3D, you really should put the origin at that point where everything's concurrent. So we really need to put the origin up here. So make that the y-axis and that the x-axis. We can leave z the way it is. It just needs to start down up there where the forces are concurrent. Now, what do we know? We know the hot air balloon is tethered, so it's got these three cables. The lift of the balloon is straight up 280 pounds. I'm going to draw on top of this and then we'll move it later. We want to determine the force exerted on the balloon by each cable. Okay, so we've got a force here, here, and here. So that's kind of what we've got to deal with. That's our little concurrent force system. Now in this one, they give us the coordinates of, let's see, they give us the coordinates based on their origin. So we do have to kind of translate what this means with our new origin. So they say that for A, let's see, make sure D, so D is 40 feet above the plane, basically. So that's fine. And then they are showing the coordinates of these individual points on the ground plane, which is the XY plane that they have. So we basically need to subtract 40 off of these points because we're moving our XYZ coordinate origin up 40 feet. So we're going to make this point 0, 0, 0, which will make A, it still goes in the X direction, it still goes 19 feet towards us. In the Y, it still goes 30, but it actually drops down from our origin 40, so negative 40. And B is 17, negative 24, negative 40. And C is negative 26, negative 16, negative 40, all negatives. So those are our actual endpoints. Let's go ahead and put those into MathCAD. Remember, one of the first things we need to do is calculate the length of these. In this case, they actually are cables, so they do have a real length. Sometimes they're just forces, and the length is related to the magnitude. But these are actual cables with a real length. So I'm going to go to MathCAD and start plugging in some of this stuff. So ours were A, B, and C. So we've got a length for, see, I've got to remember which, that's, all right, I'm trying to remember how to do a subscript. Length of A is the square root of, see, I need to see our numbers. Let me see if I can move my window in a way that I can see everything without doing that. All right, square root of 19 squared. I'm going to leave off feet for now. We'll just add, we'll add that later. Well, we can put feet. It's not going to matter, but we'll put it in there. Whoops. 19 plus 30 feet plus negative 40. And we want that in feet. Okay, and we'll do that for A, B, and C. So B is, can't see it. I think it's 17. Yeah. So 17 plus or minus or plus a negative 24. And then plus a negative 40. So 49. And then we have the length of C. And it was a negative 26 feet. Plus a, whoops, didn't want that up there. Plus a negative 16 feet squared plus a negative 40. All right, so there's all of our lengths of these cables. They're all roughly the same length, which they should be. I mean, they're all in the same vicinity, and one of them's not really far away from the others, which would make it much longer. So those are the lengths of our things. It does look like I used a lowercase c. Since I used uppercase for all the others, let's make that uppercase. All right, so the next step we would want to do is go in and begin assembling our matrices. We might write our, so if you're doing this by hand, you might go and write the equations, summation of forces in X, summation of forces in Y, and summation of forces in Z all equals 0. You might do that if you're doing it by hand, so maybe we could work on that. So in the X direction, I have all the X components times their cosines. Remember, we're doing the idea that to get the value of the X component, you take the length, in this case, times the cosine of the angle between the, well, we don't take the length, we take the force in the cable for the X component. Take the force in the cable, multiply it times the cosine of the angle of that cable and whichever direction, so X, Y, or Z. So in our equations, that would look like, we'll just call it force in cable A. Now again, I'm not going to be able to solve it this, or I'm not going to solve it this way. I'm going to solve it using the matrices, since you won't have MathCAD available. So force in cable A times the cosine of theta between cable A and the x-axis. I'm doing the summation of forces. Maybe I'll write that out. That's what we're writing here for this equation. So we would have the cosine of theta AX, for instance. But we also know that the definition of a cosine is to calculate the adjacent side over the hypotenuse, and that is the value of the cosine of whatever that angle is. So we have the hypotenuse, length of A, length of B, length of C. Those are the lengths of the hypotenuse. And X is 19, 17, negative 26. Those are the X directions for each one of those cables. So I could just say FA times, now you could, make this all variable so you could change it up. I'm going to write it kind of hard-coded in some. So it would be times 19 feet over the length of cable A. Let's see. I keep forgetting how to do length of A. So that value is the cosine of theta XA. And then we'd need the one for cable B, which would be B is 17 feet. That was the X component of B over the length of cable B. So that ratio, 17 feet to the hypotenuse, would be the cosine of the angle between cable B and the x-axis. And then negative 26 here over, well, hold on, let me get all of that, over the length of cable C. All of these have to add to 0. There are no other forces in the x direction. The only other force I have is the z direction, where the balloon is trying to lift up and these cables are all holding it down. So we would do the same thing. A again times 17. Oh, no, 30. Then notice I'm doing all pluses here, and then the negatives are showing up as some of these components are negative, like that negative 26. That's how I'm just keeping track of it. Now technically, MathCAD, I could put these equations themselves in and let it solve them, but I'm going to go ahead and manually build the matrix just so you can have that done. So negative 24 here. Let's see, negative 16. Oh, well, I forgot the FC part. What was 16? In the y direction, that adds to 0. And then let's get a little more room there. Summation of forces in z direction. Okay, so FA times, and these are all negative 40, because it's we raise the balloon 40 feet above the ground plane. So they're all negative 40 coefficients here. Whoops, I put 10. And this one will be the one that's different, because they don't add to 0. They need to add to the force from the balloon, or else the balloon is moving up or down. So either I need to put a component here of, what was it, 280 pounds pulling up, or I need to say that, well, all of these need to add together, and whoops, all of them add together to equal 280 pounds pointing upwards. and so I'm going to do it that way. Otherwise, they would all, if they put them all as 0, then I'd have no forces at all. All the cable tensions would be 0. Okay. Now, what I can do is I've kind of got it set up as a matrix right here, the A matrix. So I'm manually going to go create I got to insert a matrix. I got to remember where that, here it goes, 3 by 3. And what I want to put in the A matrix would be all of the coefficients that go with the variables. Now, I have been careful that I put all the FAs in the left column, all the FBs in the middle column, and all the although I left off FC on that one. I'm not solving it with those, so it doesn't matter, but all the FCs here, and then all the constants or the residuals on the right-hand side of the equal sign. Actually, this would be negative, wouldn't it? Because if it was on the left-hand side, it would be positive, and then when I move it to the other side, it becomes negative, so I think that's actually a negative. All right, let's put in our coefficients. So the coefficients that go with each one of the variables, in this case, would be 19, and I got to put feet. That's why I didn't want to put the variable dimensions up here, the feet, because now I have to keep writing them, but it's good to do. 19 over LA. L subscript A. And then this one would be 17 over 17 feet over, wow, I keep typing the wrong thing. 17 feet over LB. And this one's negative 26 feet over LC. And then in the middle row, I put all the coefficients that go with the summation of forces in the y direction. 30 feet. So if you had variables set up here, you could speed this up a little bit if you were doing it over and over again. We're just kind of solving it as a one-shot thing. And then the last one, we have our z equation last. Now, it doesn't actually matter if you do x, y, z in that order. You can do whatever your 3 equations are in whatever order you want. The thing that matters is that you have all of this first column representing the same variable. That's the coefficients that go with that variable. Even if it's 0, you put a 0 in there. I didn't have any that were 0. Whoops, got that in there. So there's our A matrix. Now we need a B matrix. And it's just 3 by 1. And it's going to have the things that are the constants. So 0, I should technically put pound force on that since I put pound force on the 281. And then this one is negative 280, I believe, since we moved it to the other side of the equal sign. Now, so you could do that part in most any calculators that are scientific calculators. You can put values into matrices and assign them names A and B. And then all you would do is you would do A inverse, so -1, times B equals, we're in pound force, these 3 numbers. Hopefully those are the numbers that Webwork wants. Let me check real quick. Make sure we didn't make some drastic mistake. I'm not sure why that came up. All right, there we go. I guess it didn't come up on your screen. Let's see. Yes, those are the values that Webwork is expecting. Now, some clues here. These are tensions in a cable. Cables can only support tension. They can't support compression. So if you get any numbers here that are negative, and the way that you drew your free body diagram was with tensile arrows, meaning they're pointing away from the free body. In this case, the free body is just that little circle right there that maybe represents the concurrent force system origin. That's all I really drew for the free body. But I drew all of those arrows pointing away from it, which means I assumed they were in tension. And if I calculated a cable tension that was negative, over here, one of these came out negative, then I probably made a mistake. Now, if it's a rod or a strut of some kind, then it can be negative. They can, if it's a physical rod of some sort, I can push on that, and that's fine. But if it's a string or a cable or a chain, a rope, then I can only pull on those. The other thing about these numbers here are that they came out, 143 is associated with whatever variable I lined up in this left column over here, which is FA. And the 70.7, that's in the middle column, or the second column, which I did FB. And then the last one here is associated with the last column, which I did FC. So A, B, C is the order these things came out of the matrix in. And you can do that on any calculator. So I would, there is a three-dimensional problem on exam 1. So I would make sure that I knew how my calculator was going to solve that problem for me ahead of time versus trying to figure it out, because it's listed as the last problem. You don't have to do them in order, but it's the last one on the exam. And so if you get to the end and don't have much time, then you wouldn't want to be trying to figure out how your calculator does simultaneous equations. All right, let's carry on to a new problem. There are our numbers that Webwork said. What's next? Now, I'm not going to do this one, but this one, AC and AB, those are struts. Let's see what it calls. Yeah, it calls them struts up here. So they can have a compressive load. And it does look like they're in compression. So those will have negative forces in them. This is also another one where the origin needs to be over here at A instead of back here at the pins. So this one, you need to move that origin over to point A. This is more like what a simple problem would be. The 3D one actually counts as one of the hard, advanced problems. Even though it's not hard, it's more fiddly, I guess. There's lots of little numbers to keep track of. This one counts as one of the more fundamental ones. Let's do this. Oops. Well, let's just paste it normal. All right, so two strips of plastic material are bonded together, so they're glued or they've got some double stick adhesive or whatever. The average shearing stress in the glue, so they're glued, must be limited to 950 kilopascals. So that's unusual. A lot of times you have megapascals for strength, but this is kilopascals. What length L of splice plate, so those little plates on top and bottom, is needed if the axial load carried by the joint is 35 kilonewtons and the width W is 305 millimeters. So your numbers are different, but this is what my numbers look like. So when you're doing one of these, the best thing to do is go in and try to figure out what it would look like if it was going to break. That's usually a good thing to try and figure out. So I think that for this part to come completely apart, I'm going to envision this being the failure mode. And they drew this little zigzaggy thing over here showing kind of that it's not important over there. They said that 35 kilonewtons, so 35,000 newtons is applied there. And this problem, it's a little bit ambiguous on, it kind of assumes that that since it's glued, that's the weakest link, and you don't know any other material properties other than it's some generic plastic. So it does kind of make you assume that it fails this way. This is an older problem, and that's probably one of the reasons we took it out, because it's a little bit ambiguous. But this little red area here is the glue under this edge of the plate. And so on the bottom, there would be the same amount of glue. And between them, they would be holding everything together. What's 35 divided by 2? Whatever that is. Let me put it in my little calculator. 17 and a half. And then on the bottom is the other 17.5 kilonewtons. So that's on the glue surface. So the thing you notice is that that force that would be there is parallel to that glue surface, and whenever that's true, you have a shear stress. And it does say average shear stress in the glue must be limited to 950 kilopascals. So it's giving you these hints that you're trying to do at a shear problem. So shear, remember we use tau, equals shear force over the shear area. Now we have a total shear force of 35 kilonewtons. We have an area of unknown, right? We don't know. We know this. It tells us that this is 305 millimeters. That's right there. So it tells us that in the problem. So we know that a piece of the area, there's an area on top and an area on bottom. So there's two of these. And they are each, now the picture, again, it shows this little gap in here. If you don't know anything about that gap, then it's meant to be 0. Like if there's no dimensions or nothing in the problem statement that leads you to say, oh, that gap is 3 millimeters or whatever, then just assume it's 0. You can even write that down. Now the problem in Moodle doesn't give you a response area other than the answer. But if you're working it out on paper, at the end of the exam, you're going to take pictures of all your scratch work to upload in case there's any kind of questions that, you know, need some partial credit or something like that. Just write it down. I'm assuming that gap is 0. If you feel that it would need to be known and you don't have that information, just write down your assumption. My assumption is that that gap is really tiny, and that what that means is this distance here is L over 2, and the other half of it is on the other side of the splice. So my area for the red shaded area would be L over 2 times 305 millimeters. Now I've got units all mixed up here. I've got kilonewtons and millimeters and all of this, so I need to straighten out my units. And I've got that tau. It says the shear stress is limited to 950 kilopascals. So 950 kilopascals is the maximum value that tau can have. So now I've got this equation, and the only unknown in it is L. And that's what the problem's asking for, is L. So in millimeters. So let's solve that. First I'm going to convert everything over to base units because I'm not working in MathCAD here. I guess I could throw it in MathCAD, but I'm going to work it out by hand. So 35,000 newtons over 2 times L over 2 times 305 millimeters is 0.305 meters equals 950,000 pascals. Just so you know, a pascal is a newton per meter squared. That's why I converted everything to newtons and meters and pascals. So I guess I could put newtons per meter squared. So now I can start doing some math and solve for L. So let's see. I've got 950,000. Let's move that denominator over there. So times 2. And then I've got divided by 2. And then I've got times 0.305. And so now I've got 35,000 newtons. This L is in meters and that's in meters, so those cancel out. and 2 is just a number, so it's not anything. Oh no, those become meter squared. They don't cancel out. They're meter squared, which cancels out with this meter squared. So 35,000 newtons equals, where'd my number go? Did I type it in? 289,750. That would be newtons times L. So hopefully we get 35, or well, yeah, 35,000 divided by 289,750 equals L equals 0.1208. Those units are meters though. And the problem wants us in millimeters, so multiply times 1,000 and we get 120.8 millimeters. Let's check that guy. Oh, it didn't. Oh, show me the answer. Yes, 120.7938. So 120.8 should be good millimeters. So that's in the level of one of the more fundamental ones. It does have a little bit of a trickiness into it because it's not just straight up asking you to solve for the shear stress. So this could be one of the intermediate problems also, but it's reasonable somewhere in there. If y'all come up with a question in the chat, I'm kind of keeping my eye on it, so I might notice. Let's look and see what another one would be. Let's see. This is basically the same type of problem, except this is all of them at once, right? You're doing a normal stress, you're doing a bearing stress, a shear stress, and a tear-up stress. This is actually a really good problem. This is optional 1, problem 8. This is a good one to practice all of them at once on. So if you haven't done a lot of practice other than the regular web work, this would be a good one to practice all of that first content on stresses. Optional 1, problem 8. This is more of a 2D concurrent force system, but it's 2 concurrent force systems. I think we'll pass on this one right now, but basically you've got 3 free body diagrams you can draw, depending on which thing you're solving for. You could draw the free body diagram at B, you could draw the free body diagram at C, or you could keep those connected and draw the free body diagram of B and C connected together. So you've got all of those. This one's actually a design problem. It's asking you for the wire diameter. I will do this one just because I don't know that I even put a shear strain problem on the exam, but just in case I did, let's do this one real quick. It's a quick one. All right, so what's going on here is the pink parts, yeah, they're pink on your screen. Those are rubber. And this little bracket, the U-ish upside down U, V, you know, V whatever bracket is allowed to move up and down. And it's some kind of vibration isolation bracket. And it gives you some dimensions over here in the text. Oh, I'm just looking at the problem. I want to be over here so I can draw on it. Gives you some dimensions over here in the text. And what's happening is this little bracket is shearing the rubber mounts. And you want to find the average shear strain in the rubber mounts if the rigid frame displaces 0.013 inches vertically. So what that means is it's going to end up looking like this. Well, let me draw it deformed. Again, I'm exaggerating it, but just so you can see what's going on. Whoops. So it said that basically this distance is 0.013 inches. And you can kind of see where the little rubber pieces are rhombuses now instead of the rectangles they were. And we want to figure out what amount of shear strain is in those rubber pieces. And remember, shear strain is just a change in angle. and it is just the change in this angle here. That is that gamma. That is the shear strain. How much did that rhombus shear over? So to calculate that, gamma is equal to, in this case, the thing we know is L. Oh, actually, we know W2, but we don't need that one. This distance is L equals 0.4 inches. So gamma is looking at, let's see, let's do a different color. This little triangle right here. And so gamma is that, draw it bigger. There's gamma. This is 0.013 inches, and this is 0.4 inches. So gamma is the inverse tangent of opposite side 0.013 inches over the adjacent side 0.4 inches. And as a slightly shortcut, if you didn't have a calculator that could do inverse tangent for some reason, gamma is pretty much equal to 0.013 over 0.4. So let's see what that equals. And you shouldn't have any problem actually doing the tangent, but you know, once upon a time it was hard to do tangents, I suppose. So the approximation is approximately 0.0325, and this is just a decimal. This is shear strain. So you don't have, it's a radian angle, so I guess this is radians. And I'm not sure what units, well, it doesn't even have units, so probably in Webwork, don't put even radians on there. I wonder if let me see if radians, if it cares or not. 325 radian. Yeah, it doesn't like radians, so you just put the number. And then it's happy. All right. So that's a relatively straightforward one. Let's see what else we can find before we get too far. I don't want to do too many. This one's a decent one. It's got a couple of things going on. It's normal stress and change in length. I think we'll do this one, but only maybe one of these change in length pieces, because that's more about drawing free body diagrams. So we'll do one of those, since we haven't done an axial deformation problem. All right, so we're going to do the change in length of segment BC. Okay, let's cut it open. So whenever you're doing change in length of something that's got several sections on it, what you need to do is find the section you're interested in, go to the middle of that section, so we want BC, so right in here, and cut the thing open and pick one side, either the left hand side or the right hand side, and draw that free body diagram. I'll do the left hand side. So I'll just draw this part. Okay, and then label what we have on there. So I don't know which way this internal force goes. I'm just going to draw it this way. P1 is 82 kips. Remember, a kip is 1,000 pounds, so that's 82,000 pounds. I have two separate values here for P2, so that's two separate forces. Sometimes you might have these two connected together. If they're connected, then that's a single force of whatever value, but these are not connected. These are two independent forces, each of which are 46 kips. Okay, So it looks like I have a total going to the left of 82, a total going to the right of 46 times 2, which is 92. So I actually need more force going this way for it to be in equilibrium. So all that is that's summation of forces in the x direction equals 0. So all of these forces, they're all pointing in the x direction. I've got 92 going to the left, and now I've got 92 going to the right. They add to 0, and this piece is in equilibrium. So that tells me my internal force, this guy, internal force. So that's the force that causes axial deformation in that section BC. That's the one that causes stress in that section. It's causing the strain also in that section, but the strain is changing length. All right, so internal force for section BC. And since it's drawn pointing towards the body, it's in compression. FBD's free body diagram, or I guess I could just do FB for the free body. Let me erase this so it doesn't confuse you about being part of the thing. Okay, so now I can take that 10 kips and I can use my axial deformation equation, which is delta. I'm trying to find change in length. That's delta equals FL over EA. So the internal force F is technically negative because it's a compressive force. 10 kips, I'll put 10,000 pounds. The length of just section BC is labeled as B in my diagram, which is 5 feet, which I will translate to inches. So 5 feet, there are 12 inches per foot. Okay. E, that's a material property. So we need to know what kind of material. And then in this case, they just give us E is 28,000 KSI, so 28 million PSI. So we'll put that in just as a given. Sometimes you have to go look it up. 28 times 10 to the 6 PSI. You might have to go to one of those reference sheets that I was talking about. Reference sheet 1 or 2 has the material properties, and you might have to look up something like this. A is the cross-sectional area of section BC. Let's see what we have about that. All right, so it is a 2.2 inch square, 2.25 inch square. So the area, and it doesn't say it's a tube, it's a bar, so it's solid. So the area is 2.25 inches by 2.25 inches. And we know all of those numbers. We should be able to throw them into a calculator and get our delta, which should be a shrink. You know, a delta is negative in this case because of the negative or the compressive force in that section. So let's see if we can come up with the right answer. I'm using a phone as a calculator, so it's got a little bit of issues. But we'll see if we can work it out. So, how do I store? Maybe that did it. Okay. Let's see. 10,000 times 5 times 12 divided by, I want to recall. Hey. Oh. Okay, I think that worked. And the number I get is going to be in inches. It's super tiny, though. negative 0.004233 inches. I do expect there to be, not a lot. This is a really large steel bar. It does have 10,000 pounds applied in this section, but still I wouldn't expect much. Let's see if Webwork agrees. Yes, they do. All right, so that is the correct answer. To do the rest of the problem, they've got the change in length of segment AB. So we do the same thing except, we cut here. And basically, if I looked at the left-hand side of that, only P1 is applied there. So it has 82,000 pounds of tension in that section. It's being stretched out. We also need CD over here. And we can see that it has whatever P4, 45,000 pounds of tension in that section. So both the ends are getting stretched and the middle is getting compressed. We add up all of those with the stretched being positive, the compressed being negative, and we'd get the total change in length of the bar. That would be how we do that. Maximum normal stress, since this all has a consistent cross section, the 2.25 by 2.25 square, then just whichever section has the largest stress magnitude. Doesn't matter if it's positive or negative, which would be section AB here with its 82 kips. That would be the 82 kips divided by the cross-sectional area would be the maximum stress. Okay, so there will be something, again, this is like 4 problems in one, so parts of this are very fundamental. Like if I ask just part B, that's a fundamental one. If I ask C or D, that actually could get in. D could actually be one of the harder advanced problems. Maybe not super advanced, but certainly on the harder end. Part A here, that's an intermediate problem because you have to do 2 things, but it's not that hard. It'd be an easier intermediate problem if we did that. All right, let's go back over here. Check our time. We've got time. I don't see any questions in the chat. I think we were on, where'd we go? I guess we were in optional 1. That problem was somewhere around here. We just skipped that one. We did that one. There it was. This is a bearing stress problem, and this is a relatively simple one. This is not one to be careful about, but be careful whenever you have wood pieces, because wood actually has, let's look at our reference sheet for a second. Is it in here? Let's see if I can find, that's pipe. All right, so it's on this page. I just need to rotate the right way and then zoom in. All right, so see this table, it's under my picture. I can't really highlight on this one anyway that I know how to, but it's over here. This is table A15, properties of standard structural timber. So we talk about 2x4s and 2x6s and that kind of thing, but they actually have a dressed size or finished size that is not 2 inches by 4 inches. I know there's some Webwork problems like this, but I don't think there's any exam problems. But just be careful when you're working problems with timber, because a 2x4 is not 2 inches by 4 inches. It's actually 1 3/8 by 3 5/8 inches. So it's not 2x4. I don't think I did that on the exam just because it's a picky little thing. It is true, but it is a picky thing. But there are some Webwork problems like that. This is not one of them. This one just gives you the dimensions you need. I don't think that one's particularly. That's just pretty straightforward. This is more complicated. Axial deformation. It takes some thinking. Probably would be one of the more difficult problems on exam 1. It's not hard. It would be an intermediate problem, but it takes some thinking because the rod is stretching and this little cylinder A is getting compressed. So it takes some thinking about how to go about doing that. This one is pretty straightforward, although this is a design problem. It has factor of safety in there. That might be a good one to do since it's got design, factor of safety, material properties, and concurrent. Let's do this one. It's a relatively simple one, but it's got a lot of things going on to it, which make it more interesting. Let's see, where are we at? All right, so 2 structural steel rods. So these are not cables. A and B are actually rods, which means they can have compression if they need to. They don't have to be just tension. They've got a mass. Oh, here's a little tricky part. The mass is kilograms, so that's not a force, that's a mass. We have to convert to kilograms. Sometimes Webwork can give us problems because some of the problems are written with the gravitational constant 9.8, and others are 9.81, and then I think there might be some that are 9.05 or whatever it is. So we'll use 9.8 and hope that works for Webwork. We have some angles. If failure is by yielding, so that's a clue that we need yield strength versus, so our book calls it elastic strength, but yielding versus fracture. We also, on top of that, want a factor of safety of 1.6 against yielding. Determine how big these rods are to support the weight. Both rods have the same diameter, so we got to figure out which one has the higher force and then base the calculations on that. So let's do the force first. This is 2150 times 9.8. Let's do 9.81 now that I think about it. Let's do 9.81 to give us our number of newtons that we have here. 2150 times 9.81, 21091.5 newtons. Okay. Then we have the force in B, and we have force in A. We don't know those values, but we do know, well, we know we have a coordinate system X and Y. This is a 2D concurrent force system, and we know that the angle beta is 33 degrees. We know that the picture shows beta up on top, but this is the alternate interior angle deal. Alpha is 47 degrees. So same deal, alternate interior angles. Okay. Let's set this up as a system of simultaneous equations and solve it. I will probably just write them in MathCAD and let it spit them out, since I'm not sure about my phone calculator doing simultaneous equations. So let's do X. We have negative FA times cosine 47 degrees plus FB times cosine 33 degrees equals 0. And Y, FA times sine of 47 degrees plus FB times sine 33 degrees minus 21 whatever equals 0, but I'm going to do equals 21091.5 newtons. These are also newtons. Okay, kind of ran off the screen there a little bit. So we need those two equations simultaneously solved. You could do whatever you wanted, whatever method. We'll just throw them into MathCAD and not worry about the method at the moment. So let's go to MathCAD. We'll do a solve block over here. I know you certainly can't do that on the exam. FA's 1 Newton. FB, this is my initial guess, 1 Newton. My constraints are the two equations. I'd used F lowercase a instead of doing subscripts. Cosine of 47. You have to specify that it's degrees in MathCAD because otherwise it'll think it's radians. FB times cosine 33 degrees. Control equals, to show it as a symbolic equation, FA times sine of 47 degrees. Got some extra parentheses, but it's fine. Plus, oh, wait, I left off a negative sign. Negative FA, there we go. FB times sine 33 degrees. Whoops. Equals 21091.5 newtons. I need to add newtons to this 0 up here, or it'll not be happy with that. Newtons. Actually, I'm going to leave those ends off because it is not recognizing them as units, so we'll just leave them off. So what we want to do, let's move my block down to the next page so it's not chopped up. There we go. We want answers equals find FA and FB. Why is it not okay with that? Answers equals find FA FB. Huh. I did something wrong. Wonder, oh, maybe these parentheses weren't okay. There we go. That was a problem, but now why does it think FB is a problem? Oh, because I put newtons up here. There we go. All right, so my units were, in those parentheses that I said weren't a problem, actually were a problem. Answers equal. And these are based on it being in newtons. So we have our values. It looks like the FA is the controlling one. It's the larger diameter. So let's go back. I want to write it down while I'm over here. 1796 times 10 to the fourth. Oh, 1.796 times 10 to the fourth. Okay, so that's FA. FB was a smaller number. I'll write it down, 1.46. Those are newtons. All right, so FA is the one we have to design for. Not sure what happened there. So we go in, and now it is what material? Structural steel. So now we need to go to our material properties. So let's go back over here and see if material structural steel is on here in the right units. Yeah, no, those are... No. All right, so let's look at the other. That was 2. Let's look at 1. Rotate it around. So I have 2 tables here. And one of them is US units, one is metric units. I have done everything in this problem in metric units, so let's look at that side. It's a little blurry on the screen, but there's structural steel, the second line on the right-hand side. The elastic strength tension number is 250 megapascals. So it's told us to guard against yielding, so that's elastic. Fracture would be ultimate. So 250 megapascals is the number we want. So back over here, sigma yielding equals 250 megapascals. So that's the maximum allowed, except that it told us to use a factor of safety of 1.6. So we're trying to be a little extra safe. So the real maximum we can allow is 250 divided by 1.6 megapascals. 156.25 megapascals. So now I have the stress allowed, I have the force that's going to create the stress, and I can figure out the diameter. So sigma allowable equals, I'll put allow, equals force, in this case A, over well, not the diameter, over the pi d squared over 4. So sigma allowable, 156.25 megapascals. The force that's going to create the worst case scenario is 1.796 times 10 to the 4th newtons. And then I've just got pi d squared over 4. So the only unknown in there is d, the diameter of the rod. So if I can get my calculator to solve this, we can figure it out. So let's multiply by pi, and then divide by 4. So I think, oh, but that's, okay, that's times 10 to the 6. So I think I've got d squared times 121.72 times 10 to the 6th equals 1.796 times 10 to the 4th. So let's divide that number. Oh, wow. Is that going to, yeah, 1.796 times 10 to the 4th. Let's get all these in the same units. They're all kind of weird. 17.960 divided by 121.720. So I think probably should have put this in MathCAD is what I think. D squared equals 0.1475. D is going to be the square root of that, which I don't even know where I'm going to do that at. Let's see. There's square root. .384, but that would be, that would be meters. That's pretty big. That doesn't seem right. I'm pretty certain the problem is with my using a calculator that's not a real calculator. Yeah, it wants 12 millimeters. So I'm pretty sure that something in here. Let's go over to MathCAD and solve it. I'll see if we can get it to work over there, because pretty sure that's our problem. Where's MathCAD at? There it is. All right. So let's go back to what we were trying to do. So we have sigma allowable. We'll just call it allow is equal to 156.25 megapascals. All right. We have FA at 1.796 times 10 to the 4th, and those units would be newtons. Oh. Okay. And then we have the equation that would say sigma allowable equals FA over pi times d squared over 4. Okay, and we want to solve for that. It's thinking. All right, we got one, negative number over here, so that's not right. We got this one where it did some weird stuff with some units, but let's see. Oh. Okay, so there we go. There's our 12 millimeters. Also, this little piece in here, for some reason, whenever you have units built into answers that come out of the symbolic equation solver, it doesn't handle them the way I think it should handle them. And so if you just notice when I don't define them, it says they're undefined. But just go in and say, oh, well, MPA, the variable, equals MPA, the units, and it figures it out. So that's an easy enough way to make these symbolic solutions work with units. There's probably some better way to do it, but that works. So, and there's our 12 millimeters. All right, let's go back over and see what we have left. Yeah, looking at the right thing. That's a good one for compression type stuff, more of the axial deformation stuff. This one is just for calculating the moment. This is problem 18. This is a good one for just to basic calculate the moment about some point. You probably will have one of these in the fundamental level questions where you've got some forces and it's got some point, in this case O, and you just calculate the effect of these two forces about point O. So F1 times L1 and F2 times L2. Subtract those because one's going counterclockwise, one's going clockwise, and that's your moment. So you will have something like that on exam 1. You won't have one of these. This is a 3-dimensional moment that we haven't even talked about. That is a good thing to be able to do, but it's not on exam 1. This is a centroid by integration. You will have a centroid, but not by integration. You will have one more like this. We didn't work this one. We actually worked that one, or part of that one. Go ahead and, if you haven't already, finish I think we did X sub C, do the Y sub C for this one. This we need to do, and then this might be one of the last ones we'll do today. So we talked around this, but not about this. So this is a good one to try and work on. So what we have here is we've got a beam, the little horizontal beam. This would be called a cantilever beam. I don't think we named that. So cantilever is when you have one end of the beam that's fixed, and the other end is just kind of hanging out in air somewhere. So that's cantilever. The other kind, where you have both ends supported somehow with a pin and a roller, is what we've been doing. That's a simply supported beam. So that's just terminology. This is a beam that has loads on it, but the loads are not like a single point like we've been doing. So most of everything that we've loaded has been a point. You know, we've got points, you know, they're applied at this single point in here. There's a force that's applied at this point up here. Even over here, we drew them as points. This is called a distributed load, or these are called distributed loads. And basically what you do is you just treat this like a centroid. And what you want to do, if you're given one of these problems, is, and I think there's some in Webwork, there's certainly some here, and there could be one on the exam. I'm not sure if there's, it falls into the category of stuff we've been talking about. I don't know if there's one on the exam or not. But this is, if you have a distributed load, but you want to calculate something, like calculate the external reactions, where you do the summation of moments about the pin and that kind of thing. In that equation, you want this distributed load to show up as just a point load. And the basic way it works is that this is, think of this, instead of forces, these shaded red areas, instead of forces, they're just areas. So you have 3 of them. You have this little rectangle here. You have this longer rectangle on the bottom, and you have a triangle. And each one of them has a force that is corresponding to that area, because the area here is actually representing a load that's distributed or spread out. So for instance, the rectangle on top, the one that looks more like a square, it has W1 as its height. So its height is 170 pounds per foot. And it has B as its width, 2.5 feet. So if I calculate its area, 170 pounds per foot times 2.5 feet, I got the wrong number. 170 times 2.5 is 425 pounds. So at the centroid of that little rectangle, I could represent this one. As 425 pound point load, like we've been doing. Okay. For the triangle, it has a height of 170 pounds per foot. It has a base of A is 7.3 feet. Whoops, 7.3. It is a triangle though, so area of a triangle is base times height divided by 2. So I got to divide by 2. And it represents 620.5 pounds. And then the bottom rectangle has a height of negative, so it's pointing upwards, W2, which is 35 pounds per foot. The base of A again is 7.3. So, oops. 35 times 7.3. 255. It just happens to be going upwards. Pounds. Okay. Now I have represented each one of the distributed loads that were spread out over some area. I've represented them as just point loads. So now my beam looks like this. And I need to know where exactly these are. So I drew them very carefully at the centroids of these shapes. So the 255 is at the centroid of that rectangle that created it, which is just A over 2. So, well, 7.3, so it's a weird number. 7.3 divided by 2 is 3.65. 3.65 feet. The 620, that one is from a triangle. Now, you might have to go look again at your reference materials to find the location for the centroid of a triangle. I happen to remember that the centroid of a triangle is 2/3 of its base. So 2/3 of A, 2 divided by 3 times A of 7.3 is 4.87, we'll say, feet. And then the last one is the 425. It is from a rectangle, so half of B is 2.5 divided by 2. But I'm measuring everything from the wall, so the wall over here. So I'm going to add 7.3. And this distance is 8.55 feet. So now, what I want to do, what this particular problem is asking is, if I combine all of these forces that represent distributed loads, if I combine them into a single force, where do I put it? And what magnitude is it? So the resultant is easy. I just add them up. So the resultant is, I've got 620.5 plus 425. Uh-oh. MathCAD giving me trouble. Plus 425 minus, because it's going the other direction, 255.5. So 790, I believe. And that 790 is going down. I'll just put it right here for now. So that's the equivalent force. Now I just need to know, where do I put it? So this kind of goes back to when we first started doing centroids, and I had the spheres, and they each created a moment about the axis. That's the same thing that's going on here. So if I did the 255.5, 255, start over here, 255.5 times 3.65 feet, so that'll be foot-pounds when I multiply those together. That's going around counterclockwise. So that would be a negative sign. I normally do clockwise positive. So that plus 620.5 times 4.87 feet plus 425 times 8.55 feet. That is each individual force that represents a distributed load multiplied times its moment arm measured from the wall. That I want to equal the same thing as 790 times whatever its distance is, xc. So you're just doing a centroid. You could even go the bookkeeping route with the little table with the triangle and two rectangles, and they each have an area and a xc. You could just do it that way and find the location of the centroid. You could just do that. This would be the way where we started explaining at the very beginning centroids. So now we could just solve for xc from this equation. Let's see, the answer ends up being 7.24. And the F resultant, that's just the 790 number, the total. So if you took 790 pounds, put it 7.24 feet from the wall, that's the same effect as this distributed load over here. Same effect as far as moments go. Now the beam actually responds differently to those two different things, but we aren't talking about beam deflection yet. We'll do that closer to the last part of the quarter. But this one 790 pound load placed 7.24 feet would have the same effect as our original beam with the distributed loads on it. That's the idea. Let's just quickly go through and make sure there's nothing left to talk about. Pulleys are not on exam 1. They're mainly free body diagram things. I will work one later, but they're not on exam 1. This is more a pulley type problem. This one is just a design, a little bit going on with this. This one's a little bit trickier problem with some moments and stuff. I would not work it right away unless you just really wanted to. Trusses, there will be something like this where you've got a straightforward truss and you won't solve everything, like all of the truss. It'll be set up. The truss problems are to solve a particular piece of the truss, and some of the truss problems will be set up to better use method of joints. Some of them will be set up to better use method of sections. This one is just asking you for everything, so method of joints. This one, if you were asked about like CF or one of these middle pieces, that would be a method of section problem. This one would also be look for zero force members. So CG is a zero force member. It's only one. You do have one of the content questions where it's a picture of a truss and you just have to identify the zero force members. That's all you have to do. That's one of the like 3-point ones. This is an interesting one for method of sections, because it's one of the ones where you don't actually have to solve for the reactions down here. I would practice this problem. Let's see. In fact, that might be a good one to do next time on Wednesday, if you have questions about it, if you've tried it between now and then. This is just a regular truss. Method of sections is decent on this one. This is more about a shear stress, because it's got, yeah, this is a little bit more complicated going on here. It's a good problem, but it's probably beyond the scope of what we're doing. This one would be good to visualize and try to work through. Just make sure you're doing stuff right. It's a shear stress problem. That's another part of the same problem. Actually, there's several about the same problem. This one would be a good one to practice axial deformation. This is the same problem with different stuff on it. This one is tricky on the angles. I'm not so the point of the exam is not to do trigonometry, so I don't do too many where you have to really dig into like law of sines and law of cosines to solve stuff. You will have to do sine and cosine, but not like really in-depth trigonometry to figure out angles. This one I think has some issues with its difficulty, so I probably wouldn't work this one for practice. If you want to work it for extra credit, that's fine. Same thing with this one. So once you get past like maybe number 30 on here, they get into stuff that's probably not on exam 1, or is not on exam 1 and probably doesn't help you on exam 1. All right. So if between, oh, there's a question. Will there be any problems where the force on a truss is at an angle? I can't say that there will not be, but it won't be like the one I saw in here. I think it might have been this problem. Yeah, it won't be like this. Could be true. So you might have one where the force is at an angle like this, but the rest of the truss is much simpler. Think more like, well, my internet's really stopped responding. If you had a truss with a force at an angle, maybe, well, yeah, like this, because this is actually, it looks complicated, but this is actually a really pretty straightforward problem. Practice this problem. If you have trouble with it, we'll work it on Wednesday. There are definition, true, false style questions. There's only 10 points total of that, though. So they're like 2 points. But there are some, just what's the definition of stress? What's the definition of strain? I don't know if there's any true, false or not, but there are little short answer definition ones. There is trying to label the stress strain diagram, so you have a generic empty one and you have to label the different points on there, yield strength, ultimate strength, stuff like that. You have to identify zero force members, so a picture of a truss with forces on it, where are the zero force members, you have to do that. That's the type of stuff that is on the content side, and there's only 10 points of that, so there's not a lot, but there are some like that. I also realized that I see the questions like 30 seconds after you ask them, so I will eventually answer them. Let's see. That's probably enough for today. We still do have to work out. There's a couple of people needing proctors and all that. Not too many, but there's a couple. Most of you are going to log into Zoom and take the test in Moodle. So you need an internet connection. You need Zoom. And I'll give you the Zoom link once I establish it. I haven't done that yet. But you'll just sit in your computer and you'll have your reference sheet or your book. And you'll answer the questions in Moodle, and if you do scratch work like on separate paper, you'll take pictures of that and you'll upload it to Moodle once you're done with the exam, once you've turned it all in. All right, think of stuff to ask between now and Wednesday, so that Wednesday we've got time to do some questions. Wednesday's content, the new stuff, is not on exam 1, so that's fine if we push it to the end of Wednesday. All right, I will see y'all Wednesday.